Hi, I'm doing Chapter 2 a little bit differently for our notes. Chapter 2 has information about life's chemical basis, so it's a little chemistry review, which will lead into our next chapters of talking about the chemistry of life, or biochemistry, also sometimes called organic chemistry. Our opening of the chapter talks about mercury. Mercury is a chemical, and it actually can be a dangerous chemical when it comes to humans ingesting it or getting it inside their body. It brings up the story of Jeremy Piven, who was an actor on Entourage, and actually got mercury poisoning, probably from eating too much sushi that had mercury in it. Mercury is one of the elements that we can find on Earth. This is the periodic table. And Mercury's symbol is Hg. So I'll have to find it here. There it is, number 80, found naturally in Earth's rocks, but unfortunately comes out due to erosion and human activity, and therefore can infect fish, and then as we eat fish, infect us. The problem with mercury is that it doesn't clear out of our bodies very fast, and therefore can build up to toxic levels and make us sick. This whole chart here is called the periodic table of elements. It's been around for quite a while. It's very intricate, the way all of the elements found on Earth and elsewhere, and even the ones that we can make synthetically, how they fit into such an organization, and of course the use of the human mind to think about all of this and to put it into this organizational structure. And we'll talk about some of these elements as we go, but we'll also be drawing some of their, what I like to call, ring diagrams, using the information from what we can see here. Going back to the book. And there's some bold words here that you'll see that we'll go over, but I'm going to take this area here on page 24 and do some drawings to help us understand these words. Alright, so we start off with the word atom. Sometimes the word atom and the word elements are used interchangeably, but an atom is actually one of the smallest units of an element that still has the properties of that element. Alright, so if we were to draw just one atom of an element, I'm going to pick one here. Let's see here. One of my favorite ones is, well, one of the smaller ones here, hydrogen. Hydrogen is number 1 on our list of the periodic table of elements. Atoms have a nucleus, and inside of the nucleus we're going to find protons and neutrons. A proton is a particle in an atom that has a positive charge, and a neutron is a particle in an atom that has a neutral charge. So these are commonly symbols that are used for that. There's also another particle called an electron, and electrons have a negative charge. Those are also particles in an atom. Protons and neutrons are found in the nucleus. And our periodic table can tell us how many. Hydrogen has 1. So all of these atoms, or atoms of elements here, have their protons listed right here. This is actually also called the atomic number. So we can organize all of our atoms or elements by the number of protons that they have, or their atomic number. And again, hydrogen only has 1. Some drawings will draw it out, like the one we see in the book right here, with kind of little circles in the center there to show the nucleus. But I'm going to use more numbers for convenience. Alright, so 1p would mean 1 proton in this nucleus. Now this number down here is the mass, or atomic mass. This is what one average atom of hydrogen would weigh or mass out as. Again, that is just an average. Some are a little heavier, some are a little lighter. So taking this number minus the number of protons can get us the number of neutrons. So we'll do rounding here. The number is actually 1.0079, but let's round that to the whole number 1. So 1 minus 1 is actually 0. So I'm not going to write anything there for neutrons because there are none. So once again, I'll write that out. The number of neutrons is atomic mass minus atomic number, or also remember that's called number of protons. Alright, now all of these are said to be neutral atoms as they stand right now, meaning that they have the same number of protons as they do electrons. But we'll talk about how electrons can vary actually. In my periodic table that I have here, I like this one because, well, yeah, I know there's 1 proton, therefore there should be 1 electron. But there's a number up in here in the corner in the upper right hand that says that's 1 electron in that atom. Electrons actually circle the nucleus. And I usually draw them in like that. Hydrogen only has 1, so therefore I'm only going to put 1 on there. And I'll label that for you. That's the electron. And this thing right here is called an energy shell or an energy level. So when it's all said and done, I have 1 average atom of hydrogen here. So remember drawing out what you see on the periodic table. The symbol is used a lot of times. These elements were named for a Latin name or a Greek name. So like mercury, they don't always match as nice as hydrogen does, or like carbon, nitrogen, oxygen, neon, helium. But mercury is actually has a Latin name, hydrogyrum, so that's why it's Hg. Gold's Latin name is aurum, that's why it's Au. Sodium is natrium in Latin. Alright, and there was a 1 here, and then there was a 1.0079 here. Not all periodic tables will put the electrons up in the corner, but mine does. So if I were to draw lines here, number of protons found there, electron found there, and if that's not on your periodic table, when we assume that these are neutral, we should have the same number of positives as negatives. So the number of electrons should be the same as protons, at least in the neutral state. And then the atomic mass is right there. And remember, atomic number is also the number of protons. So we have all of that information that we can gain to know about one atom of an element and to know about all of these on the periodic table. Now I can do that for a bigger one. Let me pick a bigger one here. And let's see here. How about magnesium? Symbol is Mg. It's number 12 on the periodic table. So let's divide that off and begin building magnesium again. We'll start with a nucleus. And magnesium has a number 12 here, so that's the number of protons that we will put in the middle. 12p means 12 protons. Its weight, 24.3, so let's just keep that at 24, round it down. 24 minus the atomic number is your neutrons, so that will be 12. It's not always the same number as the protons, but in this case it is. I like to switch colors and make it a little more colorful. And then we're going to draw our electrons. Now this is why I like this periodic table. When we get to the bigger ones here, with hydrogen there was just a 1 there because it's such a small atom, but with magnesium it's a bigger one, and so not all of the electrons can fit on this first energy shell. In fact, this energy shell only has enough energy to hold 2 electrons, so you'll never see more than 2 on the first shell. So with the rules of chemistry, that tells me, alright, I'm going to have to draw more than 1 shell for this. So this periodic table shows that there's actually going to be 3 shells. The first shell will hold 2, second shell 8 electrons, and last shell will hold 2. So let's put those on there. My circles aren't the best, but they'll do. So again, that first shell was 2. Just like helium, a little bit like hydrogen, has 2 in the last level, but that's it. But once we get to an atom like lithium, 2 in the first level, 1 in the third level, all by itself. That second energy shell can actually only hold 8 electrons. That one has a maximum as well. So I know I'm going to put 8 out here. I like to kind of group my electrons like this. I can count them easier than 2, 4, 6, 8. Okay, I've got my limit out there. So I've got 8, 9, 10. I've drawn 10 electrons. I need to put 2 more because I have to have 12. If you add these numbers up, that's 12, or the same number as the protons because it's a neutral atom as it stands right now. So there we go. I've just drawn an atom of magnesium just from the information right there. Alright, well, as I said earlier, for hydrogen, this is an average atom. Some are a little heavier, some are a little lighter. So we might ask, well, what actually makes an atom heavier, or what makes it lighter than the average? And the answer is, or lies with, the number of neutrons. Hydrogen does happen to be one of the atoms that occurs in nature with sometimes 1 neutron, sometimes more, sometimes none, like the average one I drew here. You may have heard of things like carbon-14 dating. That's because carbon exists with sometimes more neutrons than what the average one here, what we call carbon-12, does. Alright, so our average carbon, let's talk carbon here for a second. Carbon is the 6th atom on the periodic table. 2, 4, 2 electrons in the first level, 4 in the second. and average mass 12.011. Alright, so this is a nickname of carbon-12. So if I drew this one quickly, it would have 6 protons and 12 minus 6, 6 neutrons. 2 energy shells. Two in the first, 4 in the second. Remember, I could have up to 8 out here, but as this neutral atom stands, it only has 4 right now. So what I just drew here is carbon-12. Alright, well, what about heavier ones? You may have heard of carbon-13 or carbon-14. Let's do carbon-14 since that's a pretty common one. Still 6 protons. The number of protons, or the atomic number, really is the identifier of each of these atoms. Just like your fingerprints identify you, the number 28 really does identify nickel, or 29 identifies copper. So still in carbon, 6 protons. And if this was carbon-14, that means it has a mass of 14 instead of 12. So 14 minus 6 is 8 neutrons. It has a couple more neutrons than the other one does, which makes it just slightly more heavy than our first example. Alright, so I've drawn what are called isotopes of carbon. Alright. Sometimes these atoms can radioactively decay. For example, let me find one here that's common. You may have heard of, here it is, number 92, uranium. Sometimes uranium decays, and as it decays it gives off particles and changes into a different atom then. We can take a ratio of how much uranium is there versus how much of the new element is there, and we can get a relative age of like rocks that we find uranium in. That's radioactivity, when atoms give off particles. Radioactive decay. Here's an example. Radioactive decay can transform one element into another. For example, carbon-14, which we just drew here, is a radioisotope that decays when one of its neutrons splits into a proton and an electron. The nucleus then emits the electron, so an atom with 8 neutrons and 6 protons becomes an atom with 7 neutrons and 7 protons, which then, remember, it's the number of protons that identifies the atom, so it actually becomes nitrogen. Alright, we've talked energy levels here already. We already know that our first energy level can hold a maximum of 2. Let me bring magnesium back here. First level can hold 2, and second level can hold 8. This level can hold more, up to 16. But with atoms, one important thing is that they love to, well, either have their last energy full, or energy shell full, but they also will settle for, if they can't have the last level full, they love the number 8. They can't have 8 in the first level, it just doesn't have enough energy to hold that. But starting in the second level, if they have 8 out there, they love that. And for instance, a magnesium has 1 out here. Well, it would rather have 8 or a full level out here. And so actually this atom, I guess you could if you could give this atom human emotions, it wouldn't be very happy just hanging out like this. It wants to get 8 electrons in this last level, or fill it up, or do something. And that's where we get to the chemical activity of atoms. They just don't hang out all by themselves nicely like we see here on the periodic table. They like to have that last energy level with their electrons full, or have 8 out there. So this is where they start combining chemically with each other. And there's a couple different ways that they can do that. Except, we have an exception here, this last group here. These are called the noble gases. Helium, neon, argon, krypton, xenon, and radon. They all have either a full outer level, like helium has here with the 2 in the first level, or the rest of them have 8. And they're happy that way. They just love having that 8 in the last level. So this last group here tends to not really want to combine chemically with anybody else. And so it's kind of indicative of nobility, or nobles, not wanting to mingle with anybody else. So these guys do tend to stay happy by themselves. But others here on the periodic table, they react chemically with others. Fluorine happens to be one of our most, what we call, electronegative atoms on the periodic table. Meaning it has some of the greatest pull for electrons. Greatest pull. That has the most. Remember, we're ignoring the noble gases because they don't like to combine chemically with anybody. They're satisfied the way they are. But starting with fluorine in the corner here, it's the most electronegative. It's kind of like the bully on the periodic table. It really wants to steal electrons. So if you look in the last level, there's 7. And man, it's just 1 away from having 8 out in that second level, or having a full outer level. So it's so close. So it really does have quite an affinity for electrons, and will tend to be a bully and really pull. Moving this way, the electronegativity gets less and less, going across the periodic table like this. Alright, so that sets us up for one of our first types of bonding situations. So let's take chlorine. It's a little bit bigger one than fluorine. So I'll draw that out quick. Chlorine has 17 protons. I'm not going to worry about the the neutrons for this. The neutrons really don't matter here with chemical bonding. Our first level of chlorine has 2 electrons. Next level has 8. And the last and third level has 7. So again, you ask yourself, is this last level full, or does it have 8? No, it doesn't. It has 7. An atom that chlorine typically likes to bond with, or at least that we as humans like it to bond with, that makes our food more tasty, is sodium. And sodium is number 11 on the periodic table. It's way over here. So if I drew sodium out, it's number 11. I'll put that in the nucleus there. I'm not going to worry about neutrons at this time. I kind of ran out of room here as I'm drawing, so I'm squishing it into a small area here. And 1, 2, 3, 4, 5, 6, 7, 8. And last level has 1. So we have sodium, and we have chlorine. Alright, so if these two atoms were to come in contact with one another, chlorine being way over here, this is actually called the non-metal area of the periodic table. Chlorine's right under fluorine. And remember, fluorine is our most electronegative. It has the greatest pull for electrons. Sodium's way over here. These are called metals over here. So you ask yourself, who's going to win in a tug of war to get what they want in the last level? Well, it's going to be chlorine. Because just think about it. Chlorine only needs 1 more to get 8 in this last level. Remember I said back here, they love 8. Sodium would have to gain 7 to fill up its last level with 8. So what's easier, gaining 7 or just giving up the 1? And the answer is, well, if it just gives up the 1 here to our bully chlorine. Alright, so I'll cross that one out because that's no longer there. And now it's here. That makes things a lot easier here, just to give it up. Now its last level is the second level, and there's 8 out there. It's happy. This one only had to get 1, and it's happy too with 8. Yeah, sure, this level could hold more, but it's also happy with 8. Because chlorine gained an electron, and remember an electron is negative. We talked about that earlier. Electrons are negative. So it gained a negative particle. That actually makes chlorine charged. It's not a neutral atom like it was here. It's charged with actually a -1 charge because it gained 1 electron, 1 negative. Sodium, on the other hand, gave up a negative. So it actually has 1 more proton than it does electrons. So it puts it at a +1 charge. So what happens here, because sodium is more positive as an atom and chlorine is more negative, well, we know opposites attract. So in nature, sodium and chlorine, when this happens, will actually sit really close to one another because of the opposites attract. The positive attracting to the negative. When that happens, it's called an ionic bond. So we made a sodium ion by giving away a negative, and we made a chlorine ion by gaining a negative. An ion, I should write that down, is a charged atom. So we made an ionic bond, and we made also what we could call an ionic compound. And our book tells us compounds are molecules that consist of 2 or more different elements. So having sodium and chlorine in here, it is also a ionic compound made by an ionic bond. And basically for ionic bond, think opposites attract. All because of those pesky atoms wanting to have their last levels either full or have 8 out there. Well, there's another story to this. It's not all bad with this stealing, as we spoke of here. Sometimes atoms are kind of close to one another, and neither one is strong enough to really literally pull it away or pull the electrons away from each other. So we have another situation where they don't actually steal the electrons, they share them. So I'm going to start with, how about carbon? So remember, carbon is number 6 on our periodic table. We're not going to worry about neutrons for the moment. 2 in the first, 4 in the last. Now carbon bonds a lot with hydrogen. Makes an interesting molecule. Alright. Oops, I didn't want, yeah, that'll be fine. Hydrogen has 1 proton. For this next type of bond, I'm going to draw them really close together. Make my last shelf kind of weirdly shaped. So this is hydrogen. So hydrogen had 1 electron in its last shell. We drew that earlier. And how many more to fill this level? Well, it would be 2. So commonly, hydrogen will poke around and find atoms that would be willing to share an electron with it. And so now these 2 electrons here, 1 belongs to hydrogen, 1 belongs to carbon, will actually kind of rotate here in the middle, and both atoms will be fooled into thinking that, hey, those are both my electrons, but they're actually sharing, they just don't know it. This makes these 2 atoms sit really nice, close and tight. This is the strongest bond we can have, when they sit nice and tight and they're actually sharing electrons. Hydrogen is happy, but let's take a look at carbon. Is carbon happy? If we count them up, 1, 2, 3, 4, and then the 5th one that's shared, there's only 5 out here for carbon. So how many more does it need to get 8? Well, it actually needs 3 more. So this is commonly where carbon will join with not just 1 hydrogen, but a number of them. In this case, it's going to take 4. Remember the green, if you can see colors here, the green is the hydrogen and the black is the carbon. And so these electrons will circulate just in this area to kind of serve the purpose of both carbon and hydrogen. Same with here, here, and here. So we made what's called covalent bonds, where we have sharing going on. This is a kind of a common molecule here. It's called methane, or we can name it CH4, 1 carbon, the 1 is understood, and 4 hydrogens, methane. Carbon sets up, because wanting to have 4 bonds out here, sets up a huge area of chemistry called either carbon or organic chemistry, because we can actually make long chains of carbon and hydrogen. Those are called hydrocarbons. And they're kind of the basis for, that we'll get into the next chapter, for making the molecules that make our body, proteins, carbohydrates, and lipids or fats. A molecule forms when 2 or more atoms of the same or different elements join in chemical bonds. Compounds, when they're 2 or more different elements. How are we doing here? We've discussed ionic and covalent bonds. Down in the corner here shows some different ways that we can express that, such as drawing the ring diagrams like I've been doing, or the structural models, the pictures, using lines with the symbols, the chemical formulas, and their chemical names, which can kind of get long to say. Alright, well, our next little area talks about the hydrogen bond. So they use water as an example here. Alright, we know water is H2O. So that means I'd have to draw one oxygen and two hydrogens. So I'm going to start with the oxygen. It's the bigger one. Oxygen is number 8 on the periodic table. I'm not going to worry about neutrons. Two in the first. And 6 in the second. Because I know what's going to happen here, I am going to draw my electrons like this. 1, 2, 3, 4, 5, and 6. I'm going to separate that out. There's oxygen. Alright, then we're going to put our hydrogens on here. They are going to be covalent bonds. Hydrogens again have one proton. Remember, this is going to be a covalent bonds here. Neither one is strong enough to pull the electrons away totally. But we have kind of an issue here, an issue of unevenness. Oxygen is way over here next to our most electronegative atom. So oxygen is pretty electronegative too. Hydrogen's way over here, not very electronegative. So it's not as strong at holding on to its electrons. Well, as we see with water, oxygen is not quite strong enough to pull away the electrons. So they do end up sharing, but it's an unequal sharing, kind of like oxygen is a bully. So as our little electrons are rotating around in this area, they actually end up spending more time with the oxygen atom. Hi. I'm just doing a lecture here, so recording it. So I'm just going to keep talking. I'm not crazy. So with the two electrons here, they get pulled more towards the oxygen atom. So it's an unequal sharing. That actually makes oxygen a little more negative and hydrogen a little more positive. When that happens, well, if oxygen is a little more negative, anybody sitting over here who's positive, it's going to be attracted to it. Anybody sitting over here by the hydrogen who's more negative, well, there's going to be an opposites attract there. Those are called hydrogen bonds. And this is how groups of water molecules attract each other. This is also why we say water is a polar molecule, meaning it's still a covalent bond here, that area, but there's an attraction outside here to others who have opposite charges. It's an unequal sharing situation. So here in the book we have a good example of that. So this hydrogen, who's a little more positive, is attracted to this oxygen, who's a little more negative. When water molecules attract like that, they kind of create a surface sheen that insects can walk across and such. It's also why water beads up when it's on your car. Water is an excellent solvent with things that are charged just like itself. That's why water mixes in, like with sodium chloride. We talked about sodium chloride being charged. Water molecules, the oxygen end, who's negative, is more charged to the sodium end, who's positive. and vice versa. The chlorine end, who is negative, is more charged, or excuse me, more attracted to the hydrogen, who is positive. Opposites attract. This makes water what's called a universal solvent. It's a very good solvent. Items that are not charged, like oils, tend not to be attracted to water and therefore are called hydrophobic. That's why you don't just take water and wash oil with it, because water does not mix with it. The molecules inside are not attracted to one another. Last but not least, sometimes water molecules like this dissociate and the hydrogens separate off of the oxygens. When that happens, hydrogen atoms can go mingle with other molecules in your body and can wreak havoc that way, can start combining where they're not supposed to. So this sets us up to talk about pH. The number of hydrogen ions in a solution by themselves and not tied up in water molecules is pH, or the concentration of them. In a solution. My janitor just came in and emptied the garbages, so that's why I was talking there to him for a minute a little bit ago. Alright. There's a very nice chart here on page 32. Items that have their water molecules intact and not a lot of hydrogens running around wreaking havoc by combining where they're not supposed to, are said to have a pH of 7. So pure water has a pH of 7. Items that have a lot of hydrogens moving around and dissociated from their water molecules are said to be acidic. So they have lower numbers on this pH scale. Your stomach hydrochloric acid fluid, called gastric fluid, is very acidic. You probably, if you've ever thrown up, experienced that burning in your throat. That's that acidic nature. Too many hydrogens on the loose in that fluid. Down on this end, a higher number means more basic. There's actually, instead of hydrogen ions roaming around, it's the other end. If water is H2O, so one of these hydrogen moves off, then we're left with an OH here. So those can run around and wreak havoc too. And if you've got a lot of those, hydrogens are positive, OHs are negative, they'll run around and combine with things they're not supposed to in your body. And things that are low on the list, like ammonia, bleach, oven cleaner, drain cleaner, those are basic. And again, they can be just as bad as the acidic ones. In our body, like our body fluids, except for, well, the exceptions like the stomach fluid, most of our body fluids tend to be around 7, 7.2, 7.3, right around that neutral. Meaning not so many dissociated hydrogens and hydroxides. So this is a hydrogen ion, and this is a hydroxide ion. in your body you have molecules that can actually take up these. They're called buffers. And those are talked about right here on page 33. They can combine with a loose hydrogen or a loose hydroxide, like in this equation here, so that it's not off wreaking havoc somewhere else. So buffers in our body are very important. The end of our chapter brings us back to the story on mercury. It's kind of scary to know how much mercury is out there. There's a little area about how would you vote. Let's read that over. And don't forget, on the following pages there is a summary, a list of some of the words we talked about, as well as these end of the chapter questions, which are very important and sometimes show up on tests. So make sure you take a look at those.